class number 6 of the course of Ultrasound Physic in the Florida National University. Storage, imaging, and display. Way to improve spatial resolution. Axial resolution depends on the wavelength, and the wavelength produce different pulse length. Wavelength and pulse length are directly proportional, and little is the pulse length, better is the quality of the resolution of ultrasound. Wavelength depend on frequency. Wavelength depend on frequency. Little is the frequency, bigger is the wavelength. In other words, it's necessary to have big frequencies to have little wavelength. Wavelength and frequency are inversely proportional. More is the frequency, little is the wavelength. When you have a little wavelength, you also have a little pulse length, and pulse length divided by 2 is the formula to calculate axial resolution. In resume, more is the frequency, little is the wavelength. Little is the wavelength, little is the pulse length, and when the pulse length is little, the resolution, the axial resolution is better. To improve the axial resolution, you must use a high frequency transducer. Lateral resolution depends on the beam diameter and also of the frequency, but more important about the beam diameter. The only fault to improve the lateral resolution is to use more than one focal area. The minimum distance that two side-by-side structures can be separated and still produce two distinct echoes depend of the beam diameter, and the beam diameter is better in the focal area. The only means to produce better lateral resolution picture is to use multiple focal areas. This part is more related with computer than ultrasound, but it's something that in the ultrasound examination, in the board of ultrasound, there are sometimes questions about binary numbers. Are very easy to remember, are very easy to understand, but it's something that in general we don't care too much about that. But this is something that in internet you can have a lot of different explanations of how working the binary number. The binary number are a special number that are the number that use computers. And remember that the ultrasound machine is a computer. It's a computer with a transducer, with a beamformer, with a pulser, but after this is a transducer exactly with a mathematical operation, with a memory, and with a display like any computer. The binary numbers are numbers that only have two different characters, only ones and zeros, but with only one and zeros you can get any number. Any decimal number you can translate to binary number, or any binary number you can translate to decimal numbers. Decimal numbers are the number that we use. A little box where you can only put 1 or 0 is called a bit. This is other bit with 0. Bit is the little part. Bit is the smallest amount of digital memory. Byte is the combination of multiple bits. This is a byte. In general, byte in computer have 32 bits. The normal in computer, but in video game have a lot more. Nintendo 124. That means that have 124 bytes. But this is only in video game. Computer don't need bytes too big. 32 bits in a byte of the computer is enough. Byte is a collection of 16 and actually in the computer 32 bits. Byte is the collection, bit is the smallest quantity of memory that only can have the number 1 and the number 0. We are going to review something that is elemental. Power of 2. 2 elevate 2. 4. 2 elevate 3. 8. 2 elevate 4. 16. 2 elevate 5. 32. 2 elevate 6. 64. And 2 elevate 7. 128. This is very easy to understand because each number is the double of the anterior number. 2 elevate 1. All numbers are elevate 1. 2 elevate 1 is equal to. All number powered by 1 is the same number. In other words, is 2. The next one, 2 elevate 0. All number powered by 0 is equal 1. This is something very important to remember because the number 1 is the most important of all the numbers that we are reviewing this moment. All number powered by 0 is equal 1. 1 power of 2. We are going to review all the power of 2. The first one and the most important. 1, next 2, next 4, next 8, next 16, 32, 64, 128. Very easy. You only need to multiply by 2 the number to get the next number. To repeat, 1, 2, 2 by 2, 4, 4 by 2, 8, 8 by 2, 16, 32, 64, 128. This is the power of 2. We are going in this moment to teach you how to change a binary number in a decimal number, how to change a number that use computer and the number that we use. First at all, you put over the binary number the power of 2 from right to left. Very important, from right to left. You can see 1, 2, 4, 8, 16, 32, 64, and 128. That means that you put the power of 2 over the binary number. After this, you take only the power of 2 that represent a bit with the number 1. This go, this not, this go, this go, this not, this go, not, and not. In other words, you make a sum of 128, 32, 16, 4, and 1, because 64 have a 0, no good, and 8 have a 0, no good. You take only the power of 2 that are in a position over a number 1. And after this, you make the sum and give you the number. This binary number represents the decimal number 181. Okay, we are going to go with other number to understand better. Okay, this number here in binary number represent this number here in decimal numbers. Other example. Okay, you get only the power of 2 that have a 1. This not, yes, yes, not, yes, yes, not, and not. And after this you make the sum only of the numbers that are above the number 1. Okay, the numbers that you are going to sum are 32, 16, 4, and 2. And the number is 54. These binary numbers that are here represent the decimal number that are here. Other example, very easy example, a binary number that only have 3 ones. Okay, you count only this, this, and this, and of course the number is the number 7. Not, because have 0, only the power of 2 that represent the position of the number 1. 7. You can, in this part, you can see that I have here decimal numbers and I put binary number here. 1 in decimal is exactly 1 in binary. 2 is writing 1 0. Why? Because if you put here 1 and you put here 2, you don't count the number 1, you have equal 2. 3, the same thing, you put 1 here, 2 here, 1 and 2 equal 3. This is the number 4. Doing the same, 1, 2, 4, not, only 4 equal 4. Number 5, 1, 2, 4, 1 and 4 is 5 because 2 is over a 0 and is not in the count. 5. Looking here that all the odd numbers finish in 1 in binary and all the even numbers finish in 0. 6 is even, finish in 0. 8 is even, finish in 0. 10 is even, finish in 0. You are not sure this number represents the 10. Okay, very good. 1, 2, 4, 8. Don't go. 8 and 2 equal 10. All the even numbers finish in 0. All the odd numbers finish in 1. 6 is even, finish in 0. 7 is odd, finish in 1. All binary numbers that finish in 0 are evens. All binary numbers that finish in 1 are odds, and this is the importance of the number 1, the first number on the power of 2. Remember that you need to put the numbers, the power of 2, from right to left. We are going to make other system. This system is good to have a decimal number to a binary number. Okay, we are going to use the same example that we use the number 181. 181 divided by 2 is not exact. It's 90.5, but we don't use the fractional number, only enter number. It's not exact. You put the number 1 here. 1. You divide 90 by 2, you get 45. Is exactly? Yes, it is exactly. you put the number 0 in the other box. 0. 45 divided by 2 is 22, not exact. You put 1. 22 divided by 2 is equal 11. This is exact. You put number 0. 11 divided by 2 is not exact. 5, you put number 1. 5 by 2 exactly, same thing, number 1. 2 by 2 is equal 1. This is exact. You put the number 0. And the last one is always 1. The first number in the left of all the last number that you process is obligatory 1, because remember, 0 at the left have no word. Not exact, 1. This decimal number represented this binary number. This is the number for computers. This is the number for humans. But also this system, the binary or the decimal, represent different numbers. The same numbers in binary, the same numbers in decimals. Other example, 9 divided by 2, 4, no exact, I put 1. 4 by 2, not exact, I put 0. 2 by 2, exact, I put 0. And the last that always is 1. If you are not sure, I can put here 1, 2, 4, and 8. No good. 1 and 8 is 9. But I prefer these systems. I prefer this system to the other one. This is the screen of the computer. This is the screen of a TV. Pixels. Pixel-like bit is the smallest element of a digital picture. It's not a number. It's a color. It's a color that is in the memory called pixel. Pixel is the small element of the digital memory or the digital picture. One pixel only can have one color. Other pixel only can have one color. This is the characteristic of pixel in computer. The pixel only can have one color. But ultrasound do not use color when produce pictures. And this is for that the colors in ultrasound are grays, black, white, or grays. Each pixel can have only one shade of gray. Human only can recognize 16 different grays, and this is for that the computer don't need to use a lot of binary numbers to memorize or to record different grays. This is a little table with pixel. You can see one pixel have different color. This is the scale from white to black, a different word of gray, more bright, more dark. But the computer to memorize cannot record the color. The computer only understand binary number, and this is for that the computer assign a number to each gray, beginning with white, that is the number 0, 0, 0, and finish with black, that is represented by the number 1, 1, 1, 1. In other words, the maximum number that you can record in only 4 bits. This is the maximum number This is the minimum number, and this is the quantity of different gray that can store the machine. You need a byte of 4 bits to represent 16 gray. Why? Because the maximum is 1, 1, that is equal 15, and with the 0, 0, you have 16 different numbers that represent 16 different grays. You can see the grays. You can see here the representation of the binary number and the gray that represent. Black is represented by the maximum 111, white by the minimum 0, and different grays have different binary number. This is the same explained in decimal number, but remember, the computer do not use decimal number. The computer only understand binary numbers. This is the real. Each gray, black, white, or anything have a number, a binary number that represent the gray, because the computer cannot store color. The computer only store binary numbers. It's the screen that they put the color, not the computer. The computer only remember binary numbers. You can see another illustration, different pixels with different colors and the binary number included. Black is the maximum 111, white is the zeros. This is that is inside the computer, and the other is what you see. The screen have 525 times 525 pixels. In other words, 275 625 pixels. This is the quantity of pixels that are in the screen. Remember, each pixel only can have only one color or only one gray. 525, 525. Read zoom and write zoom. There are two different zoom. You know, zoom is something that you use to go to put bigger the area that you are interested. In ultrasound we also use zoom, but zoom sometimes is not very good, because the quality of the picture, the resolution of the picture is not better than the original when you put this zoom. This is called the red zoom. The other that is better is the right zoom, because the machine, when produce right zoom, only scan the part that the sonographer is interested. You remember the machine, and if the function are changes when the picture is moving, in other words, before you put the freeze button, this is called pre-processing. This is everything that you can change before the memory. Everything that you can change before the memory, before the picture is freeze, is called pre-processing. Of the contrary, all that you change after you take the picture, exactly like Photoshop, is called post-processing. Remember, the display is the computer where you see the picture. Pre-processing before memory. After memory is called post-processing. Pre-processing here. Post-processing here in the memory, like Photoshop. In ultrasound they call digital scan converted to the memory. I don't know why. I don't know if this is something that is valid right now, but I get in the book, memory and digital scan converted are the same in the ultrasound. Memory equal digital scan converted. Everything that you're doing before the digital scan converted is called pre-processing. Everything that you're doing after you freeze the picture, in other words, after digital scan converted, is called post-processing. Pre-processing, signal processing done before the memory process, is a function of the receiver and is called write zoom. This is the big one. This is the good one. Post-processing is the bad one. Signal processing done after the memory process. This is read zoom is bad because it's Photoshop and produce pixels, do not improve quality, and this is the problem of post-processing zoom that is called read zoom. This is the most common. In the machine in general, I see more read zoom than write zoom. Digital scan converted is the computer memory that stores echo information. Analog to digital converted, this is a part of the ultrasound machine that take the echoes from the transducer and change in binary numbers. Echoes from the transducer, binary numbers, because remember the computer only works with binary numbers. Digital analog to converter is a device that converts digital number to proportional voltage amplitude. This is the contrary. Take the binary numbers and change in amplitude. This is used to put the picture in the display, to get the picture in the TV. They get the information that is binary and change in analog information. Read zoom. Okay, this is a picture with the kidney, not a good quality picture with the gallbladder. We want to make a zoom in the gallbladder and looking what happened, appear pixels. More zoom, more pixel. In this moment you cannot see nothing, only black and gray pixel, not information. This is the problem of read zoom that produce pixelate the picture. That not happen with the write zoom. The write zoom, you make the zoom and there are less pixel. Read zoom produce pixel, write zoom do not produce as pixel as read zoom, because write zoom only scan the area that you are interested. Write is good, read is bad, but it's the most common because it's the most cheapy and the less complex. Write and read. Write before read to remember. Write is the good one. No pixel. Read is the bad one. Produce pixels. Write, better resolution. Pre-processing, write zoom is in the receiver. All that you cannot change in a freezy picture is a pre-processing function. Read, word resolution, post-processing, read zoom in the memory. All that you can change in a freeze picture is a post-processing function. Cathode ray tube. This is the explanation of how working a TV monitor. I do not use more in my class to explain this because I suppose these machines are very old and are no more in use and are not more in the RDMS. Even I recommend you to get the information and to know if in this moment the RDMS examination have question about this, but I am not pretty sure because these devices are each day in less use. The X plates, the electron beam, different part of the TV, anode, cathode, electron gun, focusing length, and different part I think is not more in the RDMS examination. Frame and fields. The TV working by lines, similar to ultrasound, but they are producing one line yes, other not, other yes, other not, until the TV is covering in totality and go to make one field. After this, produce the other line that are between the original line. This is how work a TV. When finished, this is other field, and this is called two fields, one frame. This is how working the TV, producing 30 frames by second. But there are a difference with ultrasound machine. Ultrasound machine can produce different number of frames per second depending on how you are working, depending of the dip, depending of the number of focus. TV not. TV always produce 30 frames in 1 second. Different ways to storing imaging and data. Photo paper, not more in use. Everything is binary. VCR, not more, not in production. This is something very old, not more in use. Binary numbers, computer, this is called PAC. Is the system that we use in this moment. We can use paper too, but in the hospital working with PAC, electronic memory, and the film that is similar to paper and really are not more in use. If there are people working with film, it's something that is going to disappear. It's expensive, it's not practical, and you need a lot of area of storage. The future is PAC. And the end, thank you very much.